Hello, everyone. I'm gonna start by introducing myself. My name is Fatemeh. Also, I have a nickname Arezu, which you may see somewhere. Currently, I'm a PhD student at the University of Amsterdam. I'm working with Martin Derijke, and I'm part of the AI for Retail lab. So my research interests are ranking for product search specifically, and also learning from the user interactions, which leads to fairness problems and unbiased learning to rank. So today I want to present our wisdom paper, Understanding and Mitigating the Effect of Outliers in Fair Ranking. I will just go into the presentation, but please, if you have any questions, just stop me and ask the questions. This is a work that with my collaborators, Maria Hoyes, Mohamed Ali Nejadi, and my supervisors, Sebastian Schiller and Martin Dreike. So let's start with the general objective of the ranking. So what we expect a search engine to do. So traditionally, what we wanted the search engine to do was just to order the items in their decreasing order of relevance scores to the user. So we have a user with some queries, and then we want to order the documents so that this user is satisfied with the results. So we want the most relevant items at the top of the page, followed by the non-relevant items, and that's it. So we only have one user to satisfy, and the way to satisfy this user is really straightforward. But when it comes to two-sided markets or two-sided platforms, it gets a bit different. These two-sided platforms are the ones that have two types of users, like the consumer users and then the producer users. The examples are like Amazon.com, eBay, or Bloomberg website, the news websites, where you have some news from different agencies or from different groups, and then you want to present this news to the users. So here we will have two types of users that we need to satisfy, right? The consumers who are still looking for the relevant items, and then the producers who are competing for the exposure. So these producers can be the companies who are generating the news or the products in e-commerce platforms or whatever, but the scarce resource that we want to allocate to these producer users are the ranks. Because if we just assume a list-wise ranking, the thing that we need to allocate to these users are the positions in the list. And then we, as producer users, we want to be exposed to the consumer users so that we get enough interactions. So this is what we need to allocate. Let's go to one very famous example. So here again, we have a two-sided platform. It's a job-seeking scenario where there are some people, the producer users, who are submitting their resume to this website, and then we have the hiring committees who are looking for new employees. Here in this example, we have two groups of users, the males and the female candidates. And assigned to each of these candidates, we have a relevance score. So again, let's assume the list-wise view. We know from position bias that the top ranks receive most of the exposure. So in this figure, you see the yellow bars and you see the blue bars. The yellow bars are representing the exposure for each of the rank. It's the highest for the top ranks, and then it decreases when it goes to the bottom of the list. And then you have these blue bars that shows the relevance score of each of the documents or each of the candidates. Sorry. In this example, what you see is that there's not a big difference between the relevance scores of these candidates or the two groups. But what we see is that if we go for a traditional ranking and just ranking the candidates based on the relevance score, what we get at the end is a huge difference between the exposure, the average exposure for the male group and the female group, although the difference between the relevance scores are not that high. So this is the traditional ranking, right? We have a matrix here that shows the probability of showing each of the candidates at each of the positions. And the yellow color shows the probability of 1. So here we have a deterministic ranker. Each time these employers come to the website and ask for a ranking, they will get the same ranking. And always this candidate A1 will show up at the top rank, followed by the less relevant candidates and the second group, the female group. What we argue here is that it's not fair, right? Because we have two groups. The relevance is not that different, but the exposure at the end is really unfairly distributed. So the message here is that a small difference in relevance can lead to a large difference in exposure, and this is not what we want. So what we can do, the first thing that comes to mind is demographic parity. By demographic parity, we mean that we want to distribute exposure completely equal for the two groups. So again, going to the matrix of probabilities, we will implement the ranking in a way that the candidate A1 and candidate A4, so the first, the most relevant candidates from each of the groups have the same chance of being presented at the top rank, and so on for the rest of the candidates. And yeah, here the green color for the probability is 0.5. So these two candidates have the same chance, and so on for the rest. And then we will get a stochastic ranker instead of a deterministic ranker, right? So this time when employers come to the website and ask for the rank list several times, they won't get the same ranking every time. They will get different rankings, but at the end, so the expected exposure that we calculate at the end of the day will be more fair if we take these candidates in two groups. But the problem here is that it's still not the best solution, because in this example, we might not get very bad results, but let's assume that the candidate A4 has a very low relevance score. Then we are ruining the utility for some of the employers, right? Because we will show this non-relevant candidate on the top of the page. So yeah, the problem here with this notion of fairness is that the constraint is ignorant of relevance. So let's see another solution. The other thing that we can do is to calculate the probability of exposure or probability of showing items at different positions based on the relevance of each candidate. So at the end, we want the exposure to be proportional to the relevance. This way, not all the items of the different groups have the same probability of being shown at different ranks. Sometimes you get less relevant items on top of the page. Sometimes you'll see a rank list like the traditional ranker. But again, at the end of the day, the expected exposure is proportional to the relevance expected or the expected utility of the list. So here, we will have a trade-off between the exposure and utility for some of the rankings or for kind of all of the rankings. But what we expect to do is that overall, on average, after a period of time, what we get is the same for both of the groups. Right? The exposure has been distributed based on the relevance for both of the groups, or for individual, it doesn't matter. So yeah, this was about how we want to do this, and let's assume that we know the relevance scores for now. But the question is how we should calculate this exposure. So when you go to the literature on learning to rank or on fairness, what you usually see is that the exposure is defined based on the position of the item. So the exposure of item D in a ranked ranking based on the ranking policy P is the multiplication of the priority of showing item I at position J, and then the importance of position J. So position, if you follow the position bias, the top positions are most important, and then the importance drops when you go down the list. And this is it. So the only parameter that is affecting this exposure assumption is the rank. So for this work, we had a hypothesis. So here is another example of a search engine result page. This is a page similar to what you see on Amazon.com. You have a query, a list of documents, a list of items that are all kind of relevant because the query is super general, like smartphone. But in the middle of the page, you see an item which is a bit different from the rest. So we have color tags here, we have a higher price, we have bold keywords in the title and more descriptive fields. So it kind of looks like an outlier in the page. It's a bit different. So our hypothesis was that we wanted to check if these outlier items would change the scanning behavior of the users when they come to this website. What we did was to ask participants to interact with two variations of this list. In list one, we don't have anything different. So it's just a homogeneous page. All the items kind of look alike. The price range is quite the same for all items. The rating, the format of the title, everything. And the other variation is the one that I showed you now. So we didn't say anything about outlierness or about anything that specific that they need to do. We just asked them to go to this website and just interact with the page. And we track their eye movements. So this is what we get at the end. In list one, you see this famous F-shape pattern for the eye movements, where most of the attention, most of the eye fixation goes to the top page, to the top of the page, like the 1, 2, or maybe 3 items on the top of the list. So this is expected. This is position bias, we know that. And in list 2, what we see is that everything has changed. So most of the eye fixation goes to the outlier item, on the outlier item, and around it. And we see that, yeah, it totally got the user attention. And maybe it's interesting for you to know that we did this online. So when we did this study, it was in the middle of the pandemic. So we needed to keep everything offsite. So we did this using an online eye tracker, and maybe the accuracy is not as high as a very I don't know, new device for eye tracking on site, but what we see here is so obvious that we didn't even need that amount of accuracy. So we also recorded some numbers from these experiments. This is the eye fixation in terms of the time. This is the time spent on each of the items. So if they go back and forth, it just sums over all the times that the user fixed their eye movement, their eyes on the item. This is time to first fixation. So it means that the first item that the user sees, again, in terms of time. And this is the number of revisits. We have the purple bars, which shows the first scenario, and the pink bars that shows the second scenario, and you see that when there's only position bias, when we don't have any outliers, the fixation, the time spent, and the number of revisits are higher for the top ranks as expected. And the time to first fixation is lowest for the first item. So when they come to the page, they see the first item first. But when you put just one outlier in the middle of the page, everything changes. So the fixation time, the outlier was at position 3. You see this with a little asterisk here. The fixation time, the time spent, and the number of revisits now are higher for the outlier item. And the most interesting thing for me personally was that the time to first fixation is also lowest for the outlier. So it's not like they scan the page from the beginning until they arrive at the outlier item, but when they open the page, it suddenly grabs their attention. So after all of this, we can confirm our hypothesis that these outlier items can change the exposure distribution and the scanning behavior of the user. Now we need to do something about these outliers because they're different. They're making users interact with the page differently than what we expected or what we assumed before. But first, we need to, outliers change everything. First, we need to just formally define these outliers because outliers are defined in different domains, but there's no formal definition for them in the ranking domain. So we needed to do that. So let's just assume that we have a collection of items, D1 to Dn, and then we want to call these observable characteristics of each of these items observable item feature. This is important because when we are talking about outliers, we only think about the features that are observable to users. So maybe, for example, this item is an outlier based on, I don't know, maybe the average number of impressions over the last month, but it's not observable to users. So it doesn't make the item observable outlier in the ranking because, But when we talk about observable item features, we only mean the features that are used in the presentation. So these can be, these features can be purely presentational, like bold keywords in the item description, or they can correspond to the ranking feature, like the average user ranking. So the first step for us to define the outlier or to find the outlier is to translate these items to their value of their features. You can have several features and you can use any combination of these values to calculate this or to translate these items to some values so that we can find the outlier. But let's assume for now that we are talking about a single feature. So after translating these items to some values, we need to detect the outlier among the set. We can take any outlier detection method, and how they usually work is like this. You feed them the set of numbers or the set of values, and then this outlier detection method will calculate some values named that we call outlierness degree of item. This value, that outlierness degree, shows how different this item is from the rest of the items in the set. And then in the second step, this outlier detection method will compare the outlierness degree of each of the items to the rest and decide if they're deviating enough to call it an outlier. So at the end, the result would be a binary value indicating whether item I is an outlier or not. Let's see a simple example here. Assuming e-commerce example, we have a collection of items D1 to D5. And then for the outlier detection method, you can take anything. For this example, I used interquartile based OD, which we call it M. The observable feature can be price, for example, which is observable to user, and it is an important feature when they're shopping online. So the first step, we want to translate the products to their value of the observable feature. So here is a set of prices for these items, and just with a simple look, we can guess that the fourth item is an outlier. The price is much higher, right? So when we feed these values to this outlier detection method, we get the values for the degrees of outlierness, and then based on that, it tells us which item is an outlier. The threshold can be set by the user for some of these outlier detection methods. For some of them, they use their inner assumptions, so we can change it. But from our experiments, we can see that it doesn't matter. Well, it does matter, but it's not making a huge difference when you use different outlier detection methods. Yeah, so this is basically how we find the outlier in the list. So as a summary to this point, we saw that the position-based exposure does not capture the true exposure when there are outliers in the list. And we saw that when you have an outlier, the order of examination and the probability of examination for different items change. We formally define outlier items in ranking, and now our proposal is to mitigate the outlierness of the list, because we know that these algorithms that are being used for fairness are using the position-based exposure, and this is a first step. So we're not going to estimate exactly how these outliers will change the exposure. So the easiest thing, the first step, would be to remove them from the top K item in the list, so that we can make sure that the algorithm that we have that are working with the position-based assumption still work. Yeah, so because of this, we want to make sure that we push the outlier items from the top K, and at the same time, we don't want to ruin the utility or the position-based fairness. So we want to optimize for both of these, and add another constraint for the outlierness. So going back to a stochastic ranker, just as a reminder, to optimize for a fair ranker, we need a stochastic ranking, because if we always show one item at the top, there's no way we can just distribute exposure fairly. So we need a matrix like this, showing the probability of putting each item at each of the positions. And each time the user searches for the same query, they will see different rankings of the same set of items. And one other thing about this matrix is that it needs to be doubly stochastic, because by doubly stochastic, I mean the sum of the rows and columns should equal to 1. And this is kind of obvious, right? Because the probability of putting the green document at position 1, 2, 3, or 4 should equal to 1. And again, for each of the positions, the probability of putting item green, red, white, or blue, again, should equal to 1. So the problem that we have here is to find this matrix, because when we have this matrix, we have an approach how to create the actual rankings from it. The Birkhoff von Neumann algorithm helps us do this. So given a doubly stochastic matrix like what we had, we can decompose it into actual permutations with some coefficients as the probability of showing this ranking. So A1, A2, and AN will be just 1, 0 matrices that shows the which item goes to which position, and then we have some probabilities calculated for each of these permutations. At the ranking time, what we need to do is to sample from this distribution, and just create a ranking at the end. So the problem that we are facing now is how to calculate this matrix. After that, we know what to do. This linear programming gives us this matrix if we only want to maximize the utility and satisfy the fairness constraint. So the two first constraints are for double stochasticity. The third one is just is making sure that the probabilities that we are calculating are valid. And the last constraint is for fairness, that we just implement using DTR, disparate treatment ratio, the one that we just talked about. So we want the exposure of each group to be proportional to its average relevance. This is the related work, but it only cares for the fairness. So we also wanted to mitigate the outlierness. So we need another constraint, right? Sorry.
Sorry to interrupt. I know you can't see, so I'll just speak out. I have a question on this. I guess I didn't fully understand. So if I understood correctly, the purpose of this is to generate kind of like the stochastic ranker, to simulate a stochastic ranking situation. But I didn't understand why you are also including your own a fairness constraint in this stochastic ranker.
Sure. Thanks for the question. So what we want to do is to have this stochastic ranker such that it maximizes the utility for the consumer and be fair to the producer. So as I said at the beginning of this talk, we have two types of users, the consumers and the producers. And the utility part is about the consumer users. They will get relevant items, but we also need to satisfy the producers. And what they want is enough exposure. So you need to be fair to these producers to satisfy both groups. So that is why we need this stochastic ranker in a way that that maximizes the expected utility and also be fair to the producers. So the expected exposure at the end would be similar for them for each of the groups, or for each of the groups, we will have the expected exposure proportional to their relevance.
Okay,
does that answer your question?
Yes, yeah? It does.
Can I ask a question as well?
Sure.
It links to the previous question, and it's more related to the threshold for the anomaly detection. And is it not true that, that if we change the threshold in some way, we kind of disrupt the fairness of the ranking? Because, for instance, if we choose some item that is not outlier, let's say, might be eliminated from the ranking. And in case this element is not actually conceived as outlier, might be, hurt the fairness. Is it right?
Yeah, it is definitely correct. It will affect the fairness, and at the same time, it will affect the utility as well, because this item that we removed from the list because we thought it's an outlier can be a relevant item, and when we remove it, we might even
so finding a good threshold is very important, right?
Yeah, detecting the outlier is definitely really important. And when you add more parameters to the problem, then you're adding more chance of just adding noise, right? Or
okay, yeah. That's my guess. Okay, thank you so much.
Yeah, that's a really interesting point that you mentioned. So yeah, for this work, we just assume that we know the outlierness. We use this process that I just described for detecting the outliers, and it was kind of straightforward, but we assume that these are the outliers, and after these slides, I will show you the experiments, and we did experiments with different outlier detection methods to see the effect of this noise to the algorithm. We'll get to it. So, okay, just repeating another time, we want to maximize the utility of the list for consumer users. We want to be fair for the producer users, but we know that outliers will interrupt these fairness constraints. So we want to also make sure that we're removing them from the top K. So we need another term to add to this linear programming, and for defining it, we need a vector O that shows the degrees of outlierness for items. So what we basically do is, as I showed you before, we calculate the degrees of outlierness for each of the items, and then we will put the value for items that are outliers in vector O, and for non-outlier items, we will put 0. So if there's a non-zero value in the vector O, it means that the item is an outlier, and then we want to know how much of how extreme this outlier is. So based on the degree of outlierness, we can understand how extreme it is. We also need a helper vector H that is 1 for the top K items, and then 0 for the rest of the list. And we just use this to let the algorithm know that we only care about the top K. So you can move the outlier to the position after K. We don't care where, just remove it from the top K. And then using these two vectors, we can calculate the expected outlierness of the list or the policy P. So the outlierness of collection D for the top K, given the policy P and the outlier detection method M, would be this. So we want to remove the extreme outliers from the top K. So adding this to the objective of the linear programming, we will end up at here. So we want to maximize the utility. We want to minimize the expected outlierness such that P is doubly stochastic and is fair. So this is the linear programming that we want to solve. Okay, solving that, it will give us a probability matrix, and then we can just sample actual permutations using the Birkhoff-von Neumann algorithm, and then we will have our stochastic ranker at the end. Let's see some of the results. So for the experiments, we used track fair ranking track data. So here are two plots that show the distribution of outliers in the track 2020 data. I just put this for 2019 data, it has the same pattern. So we use the number of sites. This, I don't know if you know this data, but it's a scholarly search data set. You have a query and then a set of papers. For observable feature, we use the number of citations of the paper because it is observable and it is affecting the user judgment. And when we looked at the number of citations for the rankings, you see a big variance between the minimum and the maximum number of citations for each of these documents. And this suggests that we will have a lot of outliers in the data, right? Because if the minimum and the maximum differs that much, well, it says something, and this is only for the top 20 data items in each list. And the other interesting thing is that we looked at the relevant and non-relevant outliers at the top 20 positions. And here we used 3 different outlier detection methods. We wanted just to see the degree of agreement between these methods, and later on we want to see how they affect the performance of our model. So the interesting thing is that first, you see a lot of outliers in the top 20 rank. The other thing is that most of these outliers that are documents with very high number of citations are irrelevant. So these are attractive items. People might think that these are really good papers, but these are irrelevant based on our relevance labels. So the good news is that we can remove them from the top ranks and it doesn't change anything, like it doesn't hurt utility that bad. And the other thing is that, well, it is the case for many scenarios, like even for e-commerce or for in the news search, if you are familiar with these clickbait items that are super attractive, but they're completely irrelevant. So this is something that you will see in this outlier detection for ranking. So what we did first was to check the performance of our model using different outlier detection methods. So for the initial ranker, we used ListNet. The first three column, the A model is a ListNet. It's just here for the reference. And for the other one, we used our algorithm omit for the last three rows. And as you can see, for all three models, we get better results for NDCG and for fairness. For NDCG, you don't see a big difference, but the outlierness has dropped for all of the models, all the variations of our models. And this is a good news. It means that you may get better results from some of these outlier detection methods, but it's not changing the pattern that much. So it's not that dependent, and these models are not working completely differently in the same setting. We chose this one, the COP-OD, as the method to continue with because it's parameter free and it's a really recent paper. So we get the best results from it and it's parameter free, so it's easy to use. So we will continue using this. So these are the main results. We compared our model to the baselines, to ListNet, and then FOE means only optimizing for utility and fairness, and then omit is our proposed model. We have two variations of our model, the one with soft constraint and the one with hard constraints. Yeah, if we go back to the linear programming, we have like 4 constraints for this linear programming. And the problem is that when you use the hard constraints on this row and column stochasticity, it gets so difficult that for like half of the queries, it cannot find a solution. So we need to just pass the initial ranking for those queries. But we used another version where we take the soft constraints for this stochasticity constraints, which we say that it doesn't need to be exactly equal to 1, but it needs to be less equal to 1. And then the problem that it creates is that some of the permutations we get from the Birkhoff-von-Neumann algorithms are not correct permutations, and we need to remove the incorrect permutations. But we did this as a post-processing step, and we reported the result here. We see an improvement when you use soft constraints because it helps the algorithm to solve, to find more and better probabilistic metrics for most of the queries. And yeah, so compared to the baselines, we get better NDCG, and this is, I guess we know why now, because most of these outliers that we push down the list are irrelevant. So it's not like you're losing the utility, you're even improving it, although we didn't expect it at first, but yeah, this is good news. For fairness, we don't see, we see significant improvements, but again, it's not like you're changing a lot. You still have the position-based fairness of exposure. So that's also good news. And then we have two metrics for the outliers and outlierness. So the outliers shows the number of outliers that we have in the top K, and the outlierness is calculated based on the outlierness degree. So we want to check if, for example, we have two outliers left in the top rank, but both of them are extreme and they're changing the user behavior a lot. So we wanted to also check the degree of outlierness that we have for the list. And again, for both of these, we see 82% and 80% improvement, which is a big deal.
Sorry, before you continue,
yeah.
I have another question. So I'm not as familiar with stochastic ranking. So for, in this case, NDCG, is it like aggregated over all of the different permutations? So it's like averaged. Exactly. Okay.
Yeah, exactly.
Another question I had was, in this particular case, the relevance that you have, it's given in the data set?
Yeah.
Okay, thanks.
Yeah, that was a good point. That the NDCG, the fairness, and the outlierness. So all the metrics are the expected values. So we ran the algorithm on all the queries, and then at the end we just calculated the expected amount. And this is how, yeah, a stochastic ranking works, and it is evaluated because for each of the rankings, you have a trade-off. Sometimes the fairness is better, sometimes the utility is better, but overall, if you get a fair amount of exposure for all the groups, you did a good job. Yeah, so one other point is that for outlierness, it's really important that you know what is the context. So for example, if you look at the top 10 items, one of the items might be an outlier. But if you look at the top 20 items, then you may get more similar items to that outlier. And then at the end, the algorithm doesn't recognize it as an outlier anymore. So an outlierness of an item only can be calculated based on the context. So we wanted to do to check this, the effect of the context size on the outlierness. This is the parameter n. So we looked at the NDCG at 10 and then outlierness improvement, and we changed the context from 10 to 40 because this is the maximum list size for most of our queries. So what we see is that both NDCG at 10 and outlierness will improve when you increase the context size. Because the reason why this happens is that first, the thing is that outliers are usually on the top ranks because these are, in this data set, these are the items with very high number of citations, and they're ranked high. And then when you, it doesn't matter if you just put them at the bottom of the page or in the middle of the page, when you look at the NDCG at 10, it doesn't change that much and it improves. For the outlier improvement, the thing is that if you just look at the top 10 items and then detect the outlier based on these 10 items, you may miss some outliers at the lower positions. And then your algorithm will put these outliers from the bottom of the list to the top item, to the top ranks. It can happen, right? Because you only detected the outliers in the top K, you want to put them to the back of the list, but then you have to have some items from the lower ranks to replace it in the top 10. So you may move another outlier and replace it with another outlier. So when you take the whole list as your context, you are sure that you're detecting all the outliers. And this ensures that you get a better outlierness improvement for the top 10. So the other parameter is the number of is the K in our top K setting. So we are looking, instead of top 10, we looked at top 20, top 30, top 40. And again, it is expected that we have a lower NDCG and outlierness improvement when we look at the top 40 items in the page, because it's impossible to remove outliers from the top 40, because at most you have 40 items, so you can't remove them. And for NDCG, it again have the same issue where you want to remove this outlier from the top 40 and you can't, so it just stays put and then it ruins your utility. Okay, so I guess these are the main findings of our work. As a conclusion, we just introduced and studied the phenomenon of outlierness in fair ranking. We hypothesized that the existence of outliers can change the user scanning behavior, and we confirmed it using an eye tracking study. And then at the end, we proposed OMIT, which is an approach to mitigate the effect of outliers. This is from Wisdom 2020. So we just submitted a new paper to CIR a couple of weeks ago. And in this work, we actually estimate the effect of these outliers on the exposure and on the click propensities. So yeah, fingers crossed. Maybe I can share the findings of that. Yeah, I now really want to see you guys, so I will just stop sharing for a minute. And yeah, I'm happy to take any questions.
Yeah, thank you so much for your presentation. It was super interesting. Yeah, I open the floor to anyone who has questions. For me, I was wondering, so if you kind of go back into the slides where you were talking about how you, well, you don't have to, so you can see us, but in the section in the slides where you were talking about like how you define an outlier, did you see, like, I guess I would be interested in knowing like the general patterns that you saw in the degree of outlierness, because I think that, like you said, is also really indicative of, like, let's say you have like only two items, but they're really, really like outliers. I wonder if you kind of have any intuition about that.
Yeah, thanks for the question. This is really interesting, and we're looking at it in our ongoing work. So we're again back to user studies. We are checking if the degree of outlierness affects the perception of users' perception of outlier. We published a short paper about the early results to cheer, so in that paper, we just checked two different levels of outlierness for 3 features in e-commerce, and what we saw was that yeah, it does affect the user perception. They can find bold outliers very easily. The eye fixation is higher, and yeah, they can just it can grab the attention better. But yeah, for this work, it was the very first step, so we didn't do much about this. We just take it as a binary label.
Gotcha. Does anyone else have any more questions?